Welcome back, everybody. I would like to clarify for those of you who are on Zoom that you can ask at any time your questions. You just need to write in the chat, and Zikai will ask them. I treat the questions on Zoom exactly in the same way as questions in the lecture hall, right? So you feel included in the lecture. I see a few raised hands that maybe you wanted to ask a question. So does anybody want to ask a question now? There was one, maybe I can say it out loud, that was asked on the chat. Do you need programming knowledge? I would say just a bit of Python is enough because we use PySpark, so which is a Python API in Spark. But other than that, we'll focus on SQL. We'll learn JSONic throughout the semester. So I would say just a bit of Python is nice. There's tutorials also out there. It's quite easy to learn, right? Any other questions? Then I'll just continue. All right, you're welcome. So let's continue then. Okay, so now that's the tricky part. So of course, today is not like the other days of the semester because during the semester, I'm going to teach you material. You know, we'll take it slowly. We'll go it step by step. But today is really special because what is following here is not actually, regular material of this lecture that I'm teaching you. It's more of an executive summary of information systems for engineers. What that means concretely is that two things can happen. You will be bored or you will be scared. You will be bored if you visited information systems for engineers and you'll be like, yeah, I already know all of that. And or if you didn't visit information systems for engineers, maybe you're going to be scared because, oh my God, this is so much and so on. But of course, that's 14 weeks of teaching, right? So I don't expect you to understand all of the material. What's very important to understand is that it is not necessary to have taken information systems for engineers. It is not necessary at all to understand big data for engineers because a lot of the content is actually decoupled and orthogonal. I'm only going to explain to you some very high-level things that are basically the juncture of the two lectures so that you understand. But I'm going to explain it at a very high level without going into the details. There is just one thing that I would like you to catch up with that you will need to know, and that's the SQL language. So you need to learn SQL. You're going to have exercises that use SQL that are prepared by the TA team next week. You should really do that. SQL is really easy to learn. A lot of people who are not computer scientists learn and use SQL. You will see it's very intuitive. It's not even like Python or Java. It's not a language like that. It's really a language just to query data, which is declarative. So I'm going today to motivate it and give you the high-level things, and then you will have to learn it. We have a question?
Yes, others on Zoom ask, is there an exercise section for Docker issue this week? No, we don't have offline section this week, but feel free to post any question to Moodle forums.
All right, thank you very much. All right, so with that word of warning that you should not run away if you're scared, that's absolutely no problem at all. And again, next week, we'll start with normal material at a normal speed and so on. All right, but it's my job not to scare you too much. This is Edgar Cote. He is the person who had this wonderful idea of looking at tables and making people look at tables instead of these files and directories on the system. And his idea, that was really probably the most brilliant idea that seeded the whole field of relational databases, is data independence. I'm going to repeat data independence 100 times during this semester. What does it mean? It means that you have these tables with what we call a logical data model, I'll come back to that you learn once and for all, and then you learn SQL and all that goes with it. How it's actually implemented, nobody actually cares. Or actually, nobody should care about how it's implemented. So it might be that this relational database management system is implemented on top of a file system like this, on a single machine. That's actually how it was done in the 70s. But maybe it's implemented on a clay tablet. That's what people were doing thousands of years ago. But the thing is, that actually works too. You could actually, I actually have, as my students from information retrieval know, I have a base in Antarctica with billions of elves. and they actually are able to do that. And you can give them all your SQL queries in there, they will do it. But it's going to take years to execute because they need to actually do the computation. But the spirit of data independence is that actually works. You can swap the file system for clay tablets. It's going to work just fine. Or you could also use some different devices like tablets. You could argue that in some way, spreadsheet software like Excel, LibreOffice, and so on, kind of also implements a sort of the relational model. It's not SQL, but it does have something data frames like in the newest versions of Excel. But in fact, you can view that as just a newer version of a clay tablet, right? So you can do it on a single drive that was a mechanical drive, or you can do it on top of a data center, right? So you could re-implement it with even more data in a data center. But you probably noticed one thing in there. The upper part did not change. It's still a table. It's the same model, the same table, the same language. It doesn't matter what you have down there, right? That is data independence. And this is why learning SQL is very useful, because that goes beyond just a single machine relational database. I think I even put the DNA here, you see? You can even do it on top of DNA, and that was actually done. All right, who understands data independence? Raise your hands if you understand. Okay, very good. So this is the idea. And what that tells you is, it's good we are lazy. Computer scientists are actually supposed to be lazy. You just learn the tables and the data model just once, SQL just once, and then you can reuse it no matter how the underlying engine is implemented. So that's the concrete deliverable. Now, that's true for tables, and actually it's true for the other shapes as well. You can also build systems for trees, for cubes, and so on. But of course, then the model is different. So then you have to learn trees, you have to learn cubes, and so on. But the idea is the same, that you can swap the underlying implementation for the shape. But today, I'm going to focus on tables, which is what we did in information systems for engineers. So if I really very coarsely, I would say, oversimplify things, we have 4 layers in a system. We have the language, the model, the compute, and the storage. The language, like that's SQL. The model, that's what tells you a table has rows and columns. The compute, that's basically the CPU. And yes, it sounds a bit weird, but people do actually say compute when they talk about resources in the clouds, that you book a few CPUs and machines and so on. They call it the compute. And then there is the storage, that's basically the disks and all the place that you store the actual bits of data. What's magic is that we can, I want to show you this. What we do in big data is that we move the compute and storage to a data center instead of a single machine, but the model and the language, they stay. So we can reuse tables and the same way on the data center. That is, again, data independence. Data independence tells us exactly that you just swap the compute and the storage, but the language and the model, they can stay the same for any shape you want. All right. Then I'd like to focus a bit on the model. So the model is basically telling you what data looks like and what you can do with it, right? That's the 2 components of the model. If you do a simple analogy with cooking, then the idea is that the model of cooking, that's what food looks like, something that can be eaten, right? And all the ingredients that you can have, the fruits, the vegetables, and so on. Then what you can do with it, that would be all the verbs. You can mix, pour, break, dry, bake, grill, melt, mince, mix. Those of you who cook probably have many more verbs that you can read in recipes. So that would be the data model of the model of cooking, a cooking model. And we have the same thing with data. We can also say what data looks like and what we can do with it. So what the data looks like is actually easy to explain even to primary school students, because they are already exposed to tables. That is a table. It looks like this. What I write on the left are synonyms. You might see people calling it differently. So table, I put it in bold. Maybe it's the most right one. Some people would call it a collection. It's a collection of records, for example. Some people would call it a relation, especially the mathematicians. That is the reason why it's called a relational database too. Some people might call it a relational table instead of just a table. This is all the same thing. This is what you see on the right, all synonyms of that. Okay, so that's the first thing, a table. The second thing is a row on that table. That is also an important concept in relational databases. So it's a row. It has a lot of other names. It's called a tuple by mathematicians, because actually you can model it as a tuple. It's also called a record. It's called a document in the realm of document stores, as we will see. It's also called an entity, an item. My favorite one is business object. Like, this is what the business people call it. When you have business people who have who deal with databases, they just call it business objects. So a table is a collection of business objects, right? All right, but if you hear that, you will know what it is, right? It's basically a record, a row in a relational table. Then we have, of course, columns. More commonly called attributes by database people, but you can also call it column. Some other names for that are field, property, key. You'll understand why when we actually use JSON a bit later, but these are all synonyms, right? So table, records, row, attributes. Now, one or several of the columns of the attributes are actually a bit more important than others. We call that a primary key. In that case, it's just one. A primary key is an attribute that actually identifies a record. For example, you're the tax office. You have the database of all the people who pay their taxes, let's say in Zurich. The primary key is going to be your AHV number, typically, in the tax office. It's your social security number. So you have a column, social security number, AHV number, and that's the one that is the primary key that identifies a person, right? AVS in French. So primary key, it's also called a row ID, a name, a key, so that really depends on the context. And yes, key can you use for this or for that. So this, I'm going to try to avoid it, but attributes, and one of the attributes is the primary key. It's also possible that several of the attributes together are a primary key. For example, license plates on cars, you might have two. You have the content plus the number. So in that case, you have two attributes that identify a car, right? Who is with me? All right, I didn't scare you too much yet, right? Okay, so this is the model. And finally, we have the values, or the cells, or the scalars, if you think like a mathematician, or characteristic, or a fact. So this is one single specific cell in the table. Scalar, it's interesting that some people call it scalar. I think it's a little bit the same thinking that when you have a vector space or an algebra, you distinguish. Who is familiar with vector spaces? Some of you, right? Very good. So basically in a vector space, let's say on C, complex numbers, then you have the complex numbers, they are called the scalars. The scalars as opposed to vectors, right? Then you can multiply a scalar by a vector, it's going to just resize it, and you can basically involve both of them in your vector space. There's a bit an analogy with database systems and document stores and so on, that we also have this distinction between what we call atomic types and structured types. So the atomic types would be a little bit like the scalars, and the structured types would be a little bit like the vectors, right? So this is the reason why people might call that a scalar, as opposed to records or tables that would be more structured, okay? Closing the parenthesis. So table, row, attributes, primary key, value. These are all the concepts. There is an idiom that we have, database people call them first-class citizens. First-class citizens are basically all of these. These are the concepts that are central to a data model. They are the first-class citizens. And then you might have other concepts that can be derived from the first-class citizens, but they are less at the center of the model. All right, this is what a table is. Now, what do we do with tables? A lot of things. In order to manipulate tables, I spent 1 or 2 weeks in information systems for engineers actually defining the math behind relational tables. It can very quickly become very scary, especially because there's 2 ways to do that. But you don't need to understand any of that. just the high level, because all you need to understand is really that, basically. But just for those interested, or as a brush up for those who are in information systems, you can actually view a table, which is on the left, as a mathematician, they would see it as a collection of tuples, right? It's exactly the same thing, but a mathematician here would see tuples, which are basically sequences of values, one for each column. And then the table is just a list or a set or a map of such tuples, right? For this reason, a mathematician would define a table as a relation. What is a relation? It's a subset of the Cartesian product of the domains. Don't run away, don't be scared. You don't need to understand that for big data for engineers, right? But basically, that's to say this is why it's called a relational database in the first place. But there is a simpler way instead of this, which is actually quite complex. It's also imperfect because that has a few flaws that make it not quite, so the math doesn't exactly correspond to the model. So this is why I'm not very happy with that one. But there is another way. If you remember what I told you about what a table is, I told you it's a collection of records, right? A table is just a collection of records. A record is a row. So if you see it like this, then you can define it as a collection of records. By collection, I mean a set of records, or a list of records, or a bag of records. Which one you pick depends if you care about the order. If the order of the records are actually important, then you want a list of records. If you do not care about the order of the records, then you have a set of records. For example, the tax office has a set of records. They probably don't care about the order in which they have the people in their database, right? And a bag is a bit in the middle. In a bag, you can have multiple duplicates of the same records. That is allowed. Wouldn't be allowed in a set, right? But you can allow duplicates. So set bag list, take it like a restaurant menu. You go to the Mensa, you can pick the first menu, the veggie menu, and so on, the street menu. It's like a menu you can pick from. You choose. You want a set, you want a bag, you want a list, one of the three. So collection, set, bag, or list of records. What is a record mathematically? Well, technically, it's a map. It's a map. For example, the second record, here, let me go back to this one. It's a map that maps PID to 2, last to Ramanujan, first to Srinivasa, and country to India. That's a map in this sense, right? So a record is a map that maps attributes to values. And every record is a different map. Now a map looks like this. A mathematician would use this little symbol with the right arrow and the vertical bar. They use that for functions. PID is associated with 2, last with Ramanujan, first with Srinivasa, and country with India, right? That would be just another representation of the same thing that I shown you here, right? So that is called a map. The difference, a map is similar to a function, but the difference is that a map might not map everything to something. When you have a function, typically it's full. Everything is mapped somewhere, but in a map, it's only partial. So we associate PID, last, first, and country, but nothing else than these 4. All right, so this is a map that we call a record. Now, we'll see in this lecture that we are not ever going to do that. That's what mathematicians do, but we won't do that. Instead of displaying it like this, we're going to display it like that. Has anybody seen something that looks like this? Some of you, what is it called? JSON. Yeah, exactly. That is called JSON. And we'll see how important it is in that lecture. That is a JSON representation of one record in the table, and which record? This one. Who sees that this here, the record that is highlighted, is the same as this? Very good. All right. So this is a record. It's a map. We map the attributes that are on the left-hand side of the column to values that are on the right-hand side of the column. All right. And this, so of course, in JSON, you would do it in that way. Now, it turns out that in that case, you can display it like this because it's all flat, right? We'll see that in the more general case, it might be more complex than that. So this is it. That is the intuitive display, and that is the JSON syntax, but this here is the one and same thing, right? This is the nice display. This is the JSON syntax. Now, In a table, we are going to have a collection of these. So this is just one record. What if you have 3 records, 10 records, 1,000,000 records? Then obviously, you would like these records to fit together in a table. What does it mean that they fit together? It means that they have the same attributes, right? You expect all the records. If you look at this table right here, you have 6 records. Do you agree? They all have the same attributes. They all have PID, last, first, and country, right? They fit together. This is the case of these 4. These are 3 different records. Do you agree? They all have the same attributes, PID, last, first, and country. When they do have the same attributes, we can glue them together like this, right? This is called relational integrity if they have exactly the same attributes. Who is with me? Right? This is relational integrity. This is an example where it's broken. In that case, it doesn't hold. That's not a table. Name is missing in the 2nd record. Physicist is missing in the 3rd record. And we have country that is extra in the 3rd record. So here, relational integrity is broken. And here it holds, right? It's very visual. So that is the first rule that my collection of records must fulfill if it wants to be a table. Rule number 1. Rule number 2 that it has to fulfill is called atomic integrity. What it means, remember what I told you about vector spaces, that we have scalars and vectors. In the same way here, we have the atomic values and the structured values. Well, if I want to be a table, what I want is that all of my values that are in there, this one, this one, this one, this one, this one, all of them, I all want them to be atomic. What I mean is that strings are fine. These are actually all strings in there. A number is fine. A date is fine. So all of these things are fine. What I do not want is this, because this here is not atomic. This is a table in a table. So you can have, in general, if the values are tables themselves, is nestedness, a table in a table in a table in a table. And I like to compare that with the Inception movie. Who saw Inception? Right? A dream in a dream in a dream in a dream. You can have a table in a table in a table in a table. Well, if you want the overall table to be a table, you are not allowed to have a table in a table. This is forbidden. That's broken atomic integrity. Now it's okay, right? So that is rule number 2. You cannot have structured data in the cells. It has to be all atomic values, strings, numbers, dates, and so on. Okay. And then there is a 3rd rule. Rule number 3 has to do with the columns. Everything that is in the same column has to be the same type. Here, the name is always a string. The first name is always a string. This is true or false. It's always a Boolean. And the year is an integer. So here we have what we call domain integrity. That is rule number 3. We are able here to associate every attribute with a specific type or domain, and all the values in that column must be in the same domain or of the same type. All right? 3 rules that we want together. This is where it's broken. You see, in that case, it's broken because physicist true -1 false. It's not the same type here. Year 1905, 1936, and then 42 as a string. That's also broken. Who sees that? Right. All right. So you see, this is forbidden, and this is forbidden. And if we forbid these 3 things in our collections of records, at the intersection of these 3 rules, we have the beautiful, wonderful world of relational databases. That is what a table is. All right? And in that course, we are going to drop all of that and break all of these rules. We are going to break relational integrity. We are going to break atomic integrity. We are going to break domain integrity. So we are going to have tables in tables. We are going to have collections of records that don't even have the same attributes. We are going to have collections of records that even might have different values in the same columns. We are just going to throw all of that away and break these rules. And when we break these rules, this is called NoSQL, which normally should be read as not only SQL, right? It's basically an extension of NoSQL. All right, who is with me? Very good. So all you need is this high level. Yes, maybe the microphone. If...
You can sometimes also store null in a database. Is that also called as not relational integrity?
Yes, so there's two interpretations of nulls. Basically, the first thing I should say is null is an implementation detail. It's not part of the model. It's something you find in practice when you use a system like PostgreSQL and so on. You have two ways to look at nulls. The first way to look at null is that a null in PostgreSQL means the absence of any value. It means that you could technically store that in PostgreSQL, and you put a null in there, you put a null here, and you put a null and a null, right? So that's the first way to think about it. If you think about it this way, then you would say that in the presence of a null, technically relational integrity is broken because you have missing values, if you consider that null is a missing value. That is the first interpretation of nulls. The second interpretation of nulls is that null is a value like any other, right? It's just an extra value that can belong to a domain. And you can say, for example, that a colon in PostgreSQL can be an integer or null. That's fine. Then it has domain integrity. It also has relational integrity because then null is considered a value, right? But again, I insist, null is not part of the model. It is really an implementation thing. It's in the technology, in SQL, in the system that you actually use. But that's a very good question because that's indeed a tricky point. Right? Did I answer your question? Yeah? Did I answer your question? Awesome. All right. Okay, so we made these 3 rules and spent 14 weeks on them just so that we can break them now. But not yet. Just this hour, we are not yet breaking these rules and we are still focusing on when they are enforced. And we have the beautiful world of SQL. In the beautiful world of SQL, when the 3 rules actually hold, we can define the relational algebra. The relational algebra means that we can have operations on tables and we turn tables into tables. We transform them. Just like in a vector space or in an actual algebra, in mathematics, you can have addition, multiplication, scalar products, and so on and so on. So I'm going to show you the sort of things we can do with tables. Well, that's a menu. We can union, intersect, subtract tables. We can select on tables. We can project on tables. We can rename the attributes, rename the relation. We can also shuffle data around. We can group. We can aggregate. We can sort. And then we can join. We can do the Cartesian products of tables, the join, and so on. Of course, that might be scary if you haven't seen it yet. For those who are in information systems, they already know what that means. But let me just give you a quick overview and visual of the sort of things you can do. If you've ever used a spreadsheet software, like Excel or whatever, this will be simple because you can do it in any spreadsheet software, actually. Just at your own risk, because the problem of a spreadsheet software is that if you do something incorrectly, you might actually corrupt the data. That actually happens once in a while. Governments that realize they corrupted the data because they offset the columns in an Excel spreadsheet. So you have to be careful. In a relational database management system like PostgreSQL, there's less risks that this will happen. Anyway, parentheses closed. Selection means that you take some of the records, but not all of them. For example, you might want to say, give me all of the persons that live in Great Britain, in the UK. And that would select Alan Turing and Ada Lovelace, for example. That is a selection. If you're the tax office, you might say, give me the selection of all people who live in the city of Zurich. That is a selection, all right? It selects a few rows. In Excel, you just select your whole table, you click on filter data, and then you click on the column on the little row, and you select the values you want, and Excel is going to just select the records for you. Who has already done that? Right? It's quite widespread to do. Very good. Okay, so that's the selection. That, in fact, transforms a table in another table. Now we have projection. Projection does it on the columns instead of the rows. So in that case, you say you only want to see last and first, but you no longer want to see PID and country. That is called a projection. How do you do it in Excel? You select the column and you say hide, right? And then unhide if you want to remove it. But that's basically with hiding columns in Excel, okay? That's a projection. Then we have grouping. Grouping means you want to compute the sum of some values based on a group. For example, the canton of Zurich might say, what is the total income, the aggregate income of people by Gemeinde, by city? So what you will get out of maybe, I don't know, more than 1 million people in the database, maybe less because that's the number of households actually, but let's say 1 million, is going to nicely group for every city, for Zurich, for Winterthur, for all the places in the canton. And then for every city or town, is going to give you the total income. That is called an aggregating or a grouping query. Who is with me? Right? Very popular in statistics, and this is what people do all the time. Then we have sorting. Sorting is rearranging the data. Here I'm sorting alphabetically based on first. That's also very easy to do in a spreadsheet. You click on the column and then on what you want to sort it by, ascending or descending. But this only works if my collection is a list of maps. It has to be a list because only the lists have an order. If it's a set, it doesn't make any sense. You cannot sort a set, right? It has to be a list. But I told you you can choose if you want set or list or back. So this is sorting. All right, so these ones are usually easy. Then we have the Cartesian product. The Cartesian product, very rarely used, basically associates every record in a table with every other record in the other table. You basically take all of the combinations. For example, you have 2 records in the first table R, you have 3 records in the second table S, 2 times 3 gives you 6, so you have 6 possible combinations, right? You don't even look at the data, you just take all the combinations, right? If you want to crash your laptop, do that. This is in fact how we test the exam. We try to crash it, and if so the TAs know, right? We just connect to the thing, and then we do a big Cartesian product between gigantic tables. I mean, imagine you can crash an entire data center with that. Imagine that you have a table with 1 million, let's say 1 billion records, and another with 1 billion records, and you do the Cartesian product of that. That's basically 10 to the power of 18, right? So this is a sure way to crash your infrastructure. Yes?
Yes, Edward asked on Zoom, a set itself is not ordered, but a set can be sorted by some attribute within the set.
Yes, but then you get a list. That's what I basically said. You can only have something sorted if the mathematical object you use has a sorting semantics. That's basically what I mean. So if you can, of course, sort the elements in a set, but your output will have to be a list. Or a sequence, if mathematicians would call it a sequence, right? Very good. But it's very good to think clearly. All right. Okay. So that's the Cartesian product. Now, often, what people actually do in practice, they don't want all combinations. They only want the combinations that actually make sense. So, for example, here you might only want those where B and E actually match, right? You might only be interested in this one because 1 and 1, so that you're interested in. Here it doesn't match. 2, you're not interested. This one we're interested in, and this one we are not interested. If we do that, then we only keep those that actually match, this one, and then we can, of course, keep only one column because it's B and E are the same anyway, so E I just drop. This is called the join when we do that. For example, you're the tax office. You have a table that has the people in there, the households, identified, let's say, with a phone number. Then you have a second table that contains all of the tax declarations for every year. So there's obviously going to be multiple tax declarations for every household, right? For 1 per year. Now, would the tax office do a Cartesian product of the table of people and the table of tax declarations? Probably not. That doesn't make any sense. You would basically put every person with every tax declaration. Doesn't make sense. You only want to associate a person with the tax declarations that they filled, right? Then you join between the two, right? This is the idea of a join. A join is actually a bit expensive, even though there's tricks to make them fast, but we will be able to do them in big data on top of a cluster, right? So again, this sure way to crash the cluster or to crash the machine, but if you also impose some constraints, it's called the join, and then that's something you can absolutely do. All right. I have a couple of minutes left. Again, my goal is not to scare you, so I'm going not to scare you, but basically, if I keep it high level, in information systems for engineers, I gave, as we do in every computer science curriculum all over the world, best practices, do's and don'ts. What are you supposed to do with your database? The typical use case for that is people who want to create a website with a database behind. For example, a web shop. You want to sell something like computer equipment. Typically, you set up a website with a database behind, PostgreSQL or something. Who has ever done that? Who has ever designed a website with SQL behind? Some of you, right? So it's a common thing to do. The problem is that some people do it wrong. They do it wrong because the way they store the tables are not optimal. And the problem is that if they are not optimal, it leads to all kinds of errors and anomalies. So of course, I'm not going to do into that. All I'm saying is that there are a few rules that you should normally respect when you create a database like this. And the rules have to do with, for example, the rule that the data, you cannot have tables in tables. We've seen that already. That's what we call atomic integrity, right? We've already seen that. That is called the first normal form, this atomic integrity. It's the first. And then it's like, I don't know if you have musicians, but in musicians, we like to count things. But here too, we have the first normal form, the second normal form, the third normal form, the fourth, the fifth, the sixth normal form. We even have a 3.5th normal form, plenty of them. These normal forms are just best practices that you should follow if you don't want trouble with your system. So this, we already covered the first normal form. This is why it's broken, because you have a table in a table that we don't allow, and here it's okay. In information systems, we only looked at the 3.5th normal form, which is also called Boyce code. Code is the same person, Edgar Code, who invented data independence, and Raymond Boyce is one of his colleagues. And you don't need to understand that, because again, you will see why you don't need to understand that. But if you already know what it is, it means you cannot have undesired dependency between the data. If you have like this, if you have undesired dependencies, it means your table is too big, it has too many attributes, and you shouldn't have designed such a big table. You should instead split it into smaller tables. That's the best practice according to this normal form. So if you respect this normal form, you should have a table with the people, a table with the cities, a table with the lectures, a table with the association between who visits what lecture, and so on. So it basically tells us a nice relational database should be nicely split into plenty of small tables, and each small table does one thing. This is essentially what this normal form tells us. And the reason I'm telling you it's actually relevant for this course is that in the same way that I told you we are going to break relational integrity, we're going to break atomic integrity, we are going to break domain integrity. Well, since I told you we are breaking atomic integrity, I already told you we are breaking the first normal form, right? Because atomic integrity is the first normal form. So yes, we are going to break the 3.5th normal form, the Boyce code normal form, BCNF. We are breaking it. So in big data, we don't care anymore having plenty of small tables. We just join them into a very big table and we work with that big table, right? I will explain why during the semester. So we throw that away, and we even will allow having tables in tables. So we are not even in the first normal form, we are in the 0th normal form, so 0 and F, right? So we are breaking rules, right? We are just going to throw that all away. And this is why you don't need to worry too much about the contents that we covered in information systems. It's still very useful because when you throw something away, it can still be useful to understand why you are throwing it away and what you are throwing away, right? But just on the high level, this is what it means. Any questions so far? Not in the room, not on Zoom? Awesome. So now, in terms of assignment to you, what you need to do, as I told you, you should learn SQL. The best way to learn SQL is to just try it out. So first, there's many tutorials over the internet, but the TAs have also prepared to you a beautiful exercise sheet. You will have it next week. That will be exercise 1. Exercise 0 is just to test that Docker works. Exercise 1 will be the SQL brush up. So you see, you will have time because this is only next week. So your goal is to learn it. You will see it's actually rather simple. How does it fit in all of this world of languages, because there are so many languages? Well, there's actually three worlds, I would say, with languages. There is the world of the software engineers, people who love to write code. Then there is the world of the database people. And then there is the world of artificial intelligence and machine learning, right? The one that is very hype at the moment. In each one of these three worlds, you have two levels of languages: physical level and more logical level. In the good days of the first computers, we didn't have Java. We might not even have C at the time. We didn't have all of these languages. We didn't have Python, even less. What we had was assembly code. Who has ever heard of assembly code? Right? So it's very complex, very physical. You're directly writing instructions of a very low level for the CPU. I think today nobody in their sane mind would actually write assembly code anymore. We have tools to do that. Well, some people might need that if they really want a very close control. But basically, it was what we did at the very beginning. And what we did then is we invented languages like Python, C, C++, Java, and so on, that give you a more pleasant time writing your code. It's easier, and then it gets compiled to assembly code, but you no longer write the assembly code yourself. You just compile it to it. That's software engineering. The language lets you give instructions to the computer. Now, in databases, we also have these two levels. The physical level is basically called an API. Spark is an example, PySpark. You write code in a language like the imperative language, like Python, and you use an API to transform your data. Pandas is another example of this physical level right here. But if you think of Pandas or Spark and so on, you should actually view it like the assembly code of databases. And then you have higher level languages that make it easier and more pleasant, and SQL is one of them. There's many others. Sparkle is another example for graphs. We'll have JSONic and so on. And what you will discover in this lecture is that it's more convenient to use these high-level query languages than to use these more physical level APIs. We'll learn both. We'll learn PySpark, which is a bit like Pandas too, and then we'll learn the high-level languages. And then in AI, we will not touch it, but basically we also have TensorFlow and the like that are more like the assembly code, and then higher level ways of interacting with machine learning models. We are done. See, it's already 10 a.m. So next week, I will explain a little bit SQL, and then you have the exercises. So thank you very much for visiting today's lecture. I hope I didn't scare you too much with today, and see you next week. Thank you.